presume everyone's a developer of some sort. Python. Yeah. JavaScript. Yeah. Java. C. C++. Yeah. Cool. So, anything else which is interesting? Any other language? Yep.
Go.
Go. Yeah. Go. Anybody here played around with Go? We're using Go? No? Okay, cool. So, tonight we'll talk as an introduction to Rust. But before we do the introduction, we'll go through some formalities. Thanks to Centrality, who have sponsored this. So they've provided the beer and the pizza and other things around this event. And pretty much wouldn't be as easy without those guys. Thank you guys. And also Grid AKL, they provided the space. If you guys need to use the facilities, like the male toilets and female toilets are around the back here, or there are more toilets through there, you can exit through here to go to those toilets, but you have to come back through the back over there. With the grid, for those of you who have been here before, you used to be able to come in through the main entrance. That doesn't happen anymore. They lock the doors at 5 p.m. And every meetup which is happening here will come in through these doors here. So just for future Rust meetups as well as other meetups, you can come through those doors. If there's a fire, we run down the alleyway in that direction, away from the building. And if you want to sign in, the COVID-19 sign-in sheet is there. Have I missed anything? No. Welcome. So today there's pizza. We'll have a quick break between the two talks. And just quickly, is anybody looking for a job? Developer job? Yeah. What kind of developer are you?
I'm a .NET guy.
.NET? Yeah. And you're actively looking, or?
Actively looking.
Okay, cool. Yeah. And does anybody have any jobs which are going? Simeon?
Yeah, well, our company's called Zero Earth Observation, and we are working on basically tracking ships on the sea. Interesting software as a service, and we're pretty much a startup, mostly remote. And yeah, we'll be hiring probably 1 or 2 developers, looking for both hardcore back-end systems, basically everything all the way to JavaScript in the browser.
What kind of back-end technology do you use?
So at the moment, almost entirely Go, a little bit of Python here and there. For no reason other than I decided I was going to try Go when I started there 2 years ago, and we hired a bunch of engineers, and they were like, "Well, we'll do Go." But if you love Rust and you want to come write some Rust for us, and go, "Hey, whatever."
Cool, thanks, Surian. So you're looking for a couple of developers there. Yeah.
Yeah. So yeah, maybe if anyone's interested, just chat to me after.
Is anybody else? I know Centrality, you guys are hiring?
We have one intermediate C++ or Rust developer role going, working on the blockchain team, and we have 2 community developers, senior technical roles that are more about developer relations and talking and getting people excited about our project.
Cool. And what does Centrality do?
We are a public blockchain platform that people can create decentralized apps on top of.
Cool, thank you, Nicole. So if you're interested in a Rust job, talk to Nicole. Is anybody else hiring? Any kind of developer, it doesn't have to be Rust. No. Can't say we're hiring either. But I have to say there are Rust jobs out there. Many companies are dying for Rust developers in New Zealand. So there's Zero, Centrality, and another blockchain one, which I can't remember the name of. Laminar, yeah. And there are others. So there are Rust jobs out there, but seemingly nobody's taking them. So today I'll be doing Introduction to Rust, and so will Azrael. We're going to do the same presentation over twice, so we've got the same but in different flavors. So I take more of a kind of my slant on it, and Azrael will do a very good job of his idea of Rust. For my presentation, if you have any questions, just let me know. And let's get started. So a bit about me. I'm kind of a C++, JavaScript guy who started playing around with Rust a couple of years ago, and I had some production code literally in the water for a while earlier this year. And yeah, that was written in Rust. And I found it to be a very stable, very fast, very accessible language to use. And once you get up to speed with Rust, it's very easy to use. Easy might not be it's hard to make mistakes, bad mistakes. So, yeah. So, there's a lot of love around Rust. So Stack Overflow every year do a survey of their developers. And pretty much consistently for the last few years, Rust has come out at the top. So this is last year's result. Again, this year came out at the top. I think even a bigger gap between Rust and the other languages. But this is just the Rust developers kind of saying, yeah, we love Rust, as opposed to everybody in Stack Overflow saying, yeah, Rust is a great language. So, but what it's kind of showing is those developers who have learned Rust, it really sticks out. And I mean, that sticks out. It's a little bit, but it definitely sticks out far above the other languages. And I think the other one you can compare Rust with, or some people like to compare it with, is obviously C and C++ for performance. But the other one is Go. And Go it came out at the same time. The objective at the beginning was the same, to have a nice simple language, but then Rust evolved quite significantly from its first kind of idea, and Go went its own way as well. So my presentation, I'm going to go through it kind of ad hoc. I did this a year ago. I'm reiterating these slides today. I haven't gone through them in much detail, so cool. So companies which are actively using Rust, Amazon, so they've written Firecracker. So if you've written a Lambda function from AWS, that's running Firecracker. Mozilla, if you've used Firefox, that's running Rust. At least some part of it. About a year ago, it was about 6% of the lines of code was Rust, but they want to completely move over to Rust from C++. Dropbox have been using it extensively, Brave browser. Intel developing parity with C, so that's one of the things with Rust is parity with C. So as a foreign function interface, it's always going to be able to interface with C. That's one of the primary concerns of Rust. New Zealand Fire and Emergency, of all places, have implemented Rust 0. Cloudflare have some of their microservices, serverless functions using Rust. And most blockchain companies, because they've built their platform from the beginning, they've been able to use a technology which is safe, fast, and they've used Rust. So that's Centrality, Libra, and other blockchain companies are also using Rust. So, and there are reasons for that. So there's kind of a thing which people say, with most languages, if you want it to be fast, safe, and productive, you can choose two of those. But with Rust, you can actually do all three. So you can choose, it's actually safe, fast, and productive at the same time. So, I mean, an example is JavaScript might be safe, memory safe, and productive, but it won't be as fast as C or C++. But Rust checks all of those boxes. And I think it's probably one of the only languages which does it. Actually, I'd say it's the only language which does it this way. A good example is a year ago, Microsoft looked at their bugs in their system and seeing, you know, how many of these bugs are related to memory-related bugs, and 70% of their bugs are memory-related. And these are the bugs which Rust will just avoid. You cannot actually create these bugs if you're running safe Rust. And so if they were to use, because they typically use C or C++ as well, the operating system and their applications, if they'd used Rust, you know, 70% of these bugs would have never appeared. The other part is speed. Rust is fast. So everyone likes to make benchmarks, and so there's one game called the benchmarks game, and I quite like it. It's a disclaimer. It's a game, you know, but it kind of shows you very well which languages are fast and which ones are slow. And so let's have a look. So has anybody seen the benchmarks game? So what it does is it just shows you how much slower a language is compared to another language. So they have maybe between 10 and 20 kind of toy programs, you know, like trying to solve a very simple problem that is computationally expensive. Maybe a big regex or something like that. And so what you can see over here, Ruby is about 300, or on average maybe about 200 to 300 times slower than the fastest program. And then you see Perl, Lua, another Ruby implementation, Erlang, and PHP. They're all pretty slow, you know, between about 20 to 30 times slower than the fastest program. And then we get to the faster languages, which are typically optimized quite a lot, or the architecture is such that you can write fast programs such as Node.js, Dart, which is pretty much just Node.js, Haskell, and then come all the way along and we see Go, which is about 3 times slower on average. And then we get to the 3 languages which are just the fastest languages out there, and that's C++, C, and Rust. This is all run on a Linux platform using GCC or LLVM as their compiler. But they are pretty much like one of the best optimizing compilers you can get these days. And so what that shows is Rust is fast. People say, yes, it's slower than C or C++. Yeah, maybe in some cases, but I'd say on average it would be about the same speed, or on par. As you can see, this is taken August 2019, but if you look at the most recent one, Rust is just slightly faster than C. But these always fluctuate. Take them with a grain of salt, but overall the figures kind of are true in my view. Yeah, so does performance actually matter? Because computers are getting faster, right? Well, not really. If you look at the clock speed of computers, they kind of peaked in about 2005. The clock speed of your computer, which you buy in any computer, peaked at about 2.5 gigahertz, roughly speaking. See you guys. And so it does matter, but although clock speeds not getting faster, the chips are still getting faster slightly, and that is just by using more intelligent CPU architectures and things like that, how you encode the instructions. And so, but you can also see here that around about 2005, 2004, the speed of the improvements started dropping off. And pretty much the reason for this is computers get hot, and cooling them is a big problem. So performance does matter.
I would point out that ending in 2011 isn't showing the impact of all of the speculative execution bugs.
Yeah.
And if you factor those in, it's probably like a nice dip
Yes.
in performance and then a much flatter graph.
Yeah, so what happened was, as Simeon pointed out, is to make these processors faster, they had, like Intel especially and AMD, they had to take shortcuts. And so people, in the end, what happened is people could exploit those shortcuts to grab parts of memory or expose parts of the processor, parts of other processors on the same processor, which aren't allowed. And so to get around those shortcuts, the operating system or the compiler needs to do things to slow down the computer. Either not run it in hyper-threading mode, or do other kind of things to get around these kind of problems. So yeah, it's very true. You know, like it just took a step backwards. Every time one of these bugs hits, is discovered, an implementation comes along, and sometimes you have a 10 to 20% performance impact. And one other thing to add is, you go, oh, these don't really matter, you know. But the guy who discovered the first one, I think it was the Spectre one, he demonstrated this happening with JavaScript. So with JavaScript, you could extract memory information from other processes on your computer, which is extremely dangerous when you're browsing the web anyway. So I mean, if you just search the web, is Rust really fast? Yeah, you'll see that people do, and they implement something from Node.js and do it in Rust, and it goes significantly faster. I've talked to someone who works in Paymark, and they implemented something from Java into Rust, and it used a significantly less amount of memory and worked much quicker. So this is the CPU utilization as well as the memory utilization. You can see there are significant improvements in both. One other thing Rust is very good at, and this is baked into the programming model, and that's concurrency. It allows you to do concurrency without fear without concurrency. So it allows you to program without having to worry too much about data races or things like that. So Rust uses lightweight threads. It forces you to use channels and mutexes and atomic primitives, something which a language like C or C++ doesn't force you to use. So what that means is that you're required to use safe programming practices. Yeah. So as I said, it makes concurrency simple, and it is simple. And it, like, as a C++ programmer, I'm always like, am I doing this right? You know, like, have I done this right? Have I got the concurrency right? Or like, sometimes you're like, I just want to take this shortcut. I know in most of the cases this won't create a bug, but in some cases, yeah, my program might crash horribly. But there's kind of a 1 in a million chance. But with Rust, that just doesn't happen. So you don't get those weird bugs happening. Or memory leaks. So some companies which have kind of done this or have kind of experienced this. So Google Chrome refactored their rendering engine. They tried twice using C++ and they failed. They haven't, at least a year ago, they hadn't tried again. Same with Opera, they've done the same. In Firefox, one of the product managers from Firefox told us a year ago, or a year and a half ago, he gave us a presentation on how they use Rust to actually rewrite their CSS engine, which I think is called Stylo. They tried twice using C++, and then they tried again using Rust, and they were successful. And then the Brave browser did the same as well. They rewrote something from C++ to Rust. They claim they got 69% times faster on average, but I take that with a grain of salt. They probably made some other performance improvements there. Okay, so that's kind of like my view on what Rust is pretty good at doing. And I'll just show you some code. So if you want to get started with Rust, it's pretty easy to get started. If you're running Linux or Mac OS, you can just type in that curl line in your command line, and you'll have Rust. You'll have Cargo installed on your machine. Cargo, I'll explain in a sec. And yeah, and in Windows, follow the instructions. So just go to rustup.rs. There is one interesting website which was updated today. It's called Are We Rust Yet? And so, you know, what kind of platform support is out there? You know, like what kind of targets can you use Rust for? So, you know, can you use it for web development, game development, and this explains in detail exactly where you can use it, and what you can use it for. So a good example is IDE support. So here you can see if you use Atom as your IDE, you know, you get syntax highlighting, everything except for debugging. VS Code ticks all the boxes, and IntelliJ also ticks all the boxes. Currently, yeah. So those are probably the two most popular platforms to use Rust on. And if you go through here, you can kind of see what else you can use Rust for. I'd say the weak points are GUI programming and game programming. Any other weak points? Yeah, GUI, game. I'd say those are the main ones. Web development, there are a couple of very fast web servers, or kind of to help you do web development, including in the browser. So you can compile Rust to WebAssembly and use that in quite a few different ways in the browser. So the compiler is actually called Rust-C, but as a Rust developer, you'll probably never use Rust-C by itself. You use something called Cargo, which I'll get to shortly. But in a nutshell, you can just create a file called hello.rs as a main function, a print line hello world, and it will print out hello, obviously. And so there is Cargo. So Cargo is kind of like an orchestration for your whole code library. So Cargo is like NPM in JavaScript world, or pip in Python world, but it's learned from both pip and NPM and other package managers, and it's kind of avoided the bad parts of those. I'd still say it's not perfect, but it's better than anything else I've seen. And you've got a whole bunch of packages, which is available at crates.io. So there are like almost 50,000 crates available. Crates are kind of like packages which you can just say cargo install. No, actually don't say cargo install. You just add the crate to your TOML file, which kind of explains you want this crate and this version, and then the next time you compile your project, it will download that crate if it needs to and put it into your project. It's very, very simple to take crates and install them. And I think this is a killer part of Rust. It allows you to develop, especially when you're coming from C++ world or C world, it allows you to develop fast, complex applications very efficiently. So just as an example, rand, you would put this rand equals 0.7.3 into your cargo.toml, and when you do that, it will download rand and compile it, and then you can use it in your code, that package. And then it's very easy to publish a package if you want to. So you can build your package, you can publish your package, and then it gets published to crates.io. Does anybody have any questions so far? And creating a new project is as simple as saying cargo new space demo, or the name of your project, then cargo build, and then cargo run. Although cargo build is optional, because when you do cargo run, it will run it. And I'll just quickly demonstrate this. So if I go cargo new demo, cd demo ls, so where you can see it created my cargo.toml file in a source folder, and you can see in that source folder it has a main, and you can see it's that one there. So this is all created just here, so you can just go cargo, run, and it outputs hello world. This is all from the compiler, and this is just the output of hello world. What you'll now see is you'll see a target folder there, and in that target folder is a debug folder, which is where my executable is. So I can actually run the executable from there, and it outputs demo. So that's kind of how Cargo lays out your default file structure. Yep.
I think about your previous slide. The crate.io is a public registry. Does Rust support some kind of?
Okay, so I'll quickly go through the basics. So variables this won't actually compile, because so what we're doing is we're creating a variable called x, we're adding 1 to it. By default, x is immutable. If you want to make it compile, you will get an error message like this. And I have to say the Rust compiler error messages are just the best. You know, like they will show you exactly what the problem is and what the source of that problem is in color. In color, I know. I mean, if you use GCC or something, yeah, you have to use a colorizer to do it. The guy who actually wrote these error messages, he gave a presentation here once upon a time, and So this is very useful, extremely useful to find this. But I mean, if you're using an IDE which supports Rust Analyzer or something like that, like VS Code, or most of the IDEs available, they will actually tell you, but as you're typing, that this is not valid. And then, so what we need to do, by default, variables are immutable, so we need to make the variable immutable, which is just by putting that MUT at the beginning of it. So, I mean, it's got all the standard data types, integers, floats, tuples and arrays, strings and vectors, and they kind of look like this. So you can explicitly annotate a variable. So you can say it's a F32, which is a floating 32-bit floating point. Or you can imply, you can have the compiler imply what it is. So X is implied to be a 64-bit floating point. And this is not based on your architecture, this is based on the compiler. So no matter which architecture you target, even a 32-bit architecture will still go to float 64. And yeah, you can, one thing to know about strings in Rust is that a string in Rust is UTF-8, which most languages don't do that natively, which makes it a bit more complicated if you want to say, give me the nth element of a string, because UTF-8 is not character for character. So you can always say, yeah, give me the nth element, but you just have to realize in the background, your program will actually iterate through every single element, and it's quite slow to say, give me the nth element. So there are a few things you have to kind of learn about how Rust behaves, just like any other language, how it behaves in the background. Functions are pretty simple. Rust is a very kind of, like, it takes a functional approach for many of its ideas, paradigms. And I mean, so this add5 function takes in a float 32, returns a float 32, and what you'll see there, it doesn't actually say return a plus 5, it just says a plus 5. So the last line without a semicolon is what the compiler or what the program will return on the function. Comments are just usual. You have if statements, like usual. If statements don't have the brackets around because you don't really need brackets. There are some nice things about if statements. The compiler is pedantic, so whatever's in the if statement needs to be a Boolean. It cannot, like in most languages or many languages, you can say, actually this is a number, and if it's 0 or 1 or something, do something, but it actually needs to be a Boolean type. An if statement, you can actually return a value as well. So in this case, you can see let number equals if condition 5 or 6. With many languages like JavaScript and C, you can do this in one line as well using the question mark condition. But I actually prefer this one because it means you can have a complex if statement and it actually looks, it makes sense. So other cool things are, it has a match feature. It's kind of like your switch statement, switch case. Here you can kind of match on a number, and the matches are exhaustive. So you need to include every single match in your match statement. And this makes sense when you use enumerated types. So if you have 5 enumerated types, you need 5 statements in there. Or you need a catch-all statement, which is the underscore, which just says, it's kind of like your default statement. Like an if statement, a case statement or a match statement will actually return a value as well. So you can say something like number is equal to match number, or some kind of value is equal to match, whatever. Any questions? Nope. You get your loops. You get your for loops as well. Cool thing is, again, a loop can actually return a value. So here you can see it will actually return a value called like when you break, which is quite nice to use that as well. It has your while loops. It has your for loops in kind of like for number 0 to 10. So it iterates through all of those to everything excluding 10. And then you can also use iterators. So you can turn an array or a vector into an iterator and then iterate over those elements. No questions so far? Cool. I'll see how we're going with time. I don't want to make this too long. So that's fine with Rust. Like, it's got some nice features, but there are also some kind of new like paradigm shifts, which you need to think about Rust. It has some things there are some things in Rust, such as ownership and lifetimes, which almost no other language has. And this is, I think, what makes Rust so powerful and safe. But it's worthwhile if you start to learn Rust to get your head around ownership and lifetimes. And they go hand in hand. And so ownership, what ownership is a variable owns a value. And it will always own that value, and only one variable will own that value. And you can pass that value to another variable, and then that other variable will own that value. And so you'll only ever have one owner. And so what that means is, if you want to change that value, the owner has a responsibility to allow someone else to change that value. And so the beauty about that is when the owner goes out of scope, then the value can be dropped, and then the memory can be released. So this is what's called in C++ resource acquisition. Resource initialization is acquisition, and it uses a kind of the C++ model of doing that, but it's throughout the language. With C++, it kind of, you can do things not in the C++ default way. You can do things in the C way, and get memory leaks. So I'll give you an example of ownership. So here in the main function, we're creating a string, which is actually put onto the heap, called s, with a value of hello, and then we print out s, and then we move the value s to t, and then t becomes the ownership. T becomes the owner of the value, and then we print out t. And after the point of using t, s is not allowed to be accessed anymore unless we reassign a value to it. So this will compile fine. But here, what we're trying to do, we're now trying to access S after we've assigned the value of S to T. And that won't compile. It will give you a nice error message saying that the value borrowed here after a move. And so what that means is the value of S is actually trying to be accessed, but the value is actually moved out of S to T. And then it kind of gives you a trace back to where all the moves happen. Yeah, so this is Rust magic sort, I think. So one thing this gives you is memory safe guarantees without a garbage collector. And I think this is where, so you get the kind of the memory safety of something like JavaScript or Go or other languages with garbage collectors. But you get the performance of C and C++. And the beauty about this ownership model is that it also works across threads. So when you can move an element from one thread to another thread, and once you've moved it, you cannot access it in your previous thread again. And this is all done at compile time. It's not done at runtime. So you cannot even compile your program, as we saw before. You cannot compile your program when you've moved your value from one, when you're kind of playing around getting the ownership wrong. And this is something which, when you're first learning Rust, it does take some effort to master, and you need to think about how you're doing it. And yeah, any questions? Yep.
So if you return a value from function, actually a new value is being created, and how does it work? Because
yeah, so there are a couple of ways to get around that. So that's where lifetime. So one thing which you can return from a function. So when you return a value from a function, if that value was created in that function, it gets returned and it gets moved out of that function. So it gets moved, it doesn't get copied. And so then the compiler will go, okay, this function has returned a value, and when the owner goes out of scope, whoever retrieves that value, then they'll drop it. You know, like when that owner goes out of scope, then that value gets dropped, so the memory gets cleared. If you want to, I'll go into this a bit on the next slides. So yeah, it's called borrowing as well. So there are two types of values. So you get your copy values, which natively they're generally created on the heap, no, on the stack, sorry. And these values, they'll always get copied. So let A equals 42, let B equals A. So in this case, because A is a very primitive value, it actually gets copied to B. Because it's so small, I mean, it's just as big as a pointer or a reference, or even smaller than a pointer or reference, it gets copied. And so what that means is that A is the owner of 42, and B has a value of 42 as well. And then you get the other values, which are the move values, which are, this is how I represent it. I don't know how it's called in the real Rust world. And these values are generally on the heap, and the reference gets moved from one item to another. And I'll go into a bit more detail of that. If you want to copy a string, string implements something called a copy or a clone. And you can, if you want to actually copy that string, you can just say string.clone. And that will create a copy. and then in this case, S will own hello, and T will own a copy of hello, which is not related to the hello in S. The other way to do it is to borrow it, and borrowing is slightly different. So in this case, again, S has hello, and here what we're giving T a reference to S, and T is allowed to use that reference to S as long as it doesn't mutate it. So it gets a read-only reference to S. So the compiler knows it's got a read-only reference. It can't mutate it. So it's very limited in what it can do. And so T cannot go, the scope of T cannot be longer than the scope of S. Or the lifetime of T cannot be longer than the lifetime of S. I won't go into lifetimes today. They're kind of another topic. And you can just keep on doing this. So you can make many immutable copies of, not copies, these are borrows. You can borrow values many times immutably. And you can also borrow a slice. A slice is a little part of S. So you can kind of borrow a subset of S.
Will this mean if the original string gets changed, it will be instantly reflected on the borrowed string?
Sorry?
So if we, it will be, yeah, so I'm speaking about that if value of S will be changed, it will not be reflected into that T.
No, so the thing is, it's immutable. So you cannot borrow mutably. So you cannot change S.
No, I mean if the original string gets changed.
Yeah, okay, so that's another rule. You cannot have if you have borrowed T, you cannot have a mutable version of T or S. You cannot mutate it. You can't do that.
Well, you can, but you have to jump through hoops. And
Yes.
By default, you can't.
Yeah. So if you want to do that, you need to encapsulate it inside something which allows you to give access at certain times. So if you want to mutate S or T, you can do that, but you need to encapsulate it inside a box or some other kind of object. Yeah. Yeah.
I use S after that print statement because I assume that's like a function.
So yeah, so
S is passed into that function.
Yeah. So this function only. This function, funny enough, this is not actually a function; it's a macro. So in Rust, whenever you see the Printline exclamation mark, anything with an exclamation mark at the end is a macro. And a macro is kind of, do you know of macros in C? Or so a macro kind of is meta programming. So you kind of you can kind of program the programming language.
Code generation.
Yeah, it's code generation. Yeah. Structured code generation.
Substitution in Rust. That's a key difference between Rust and C. Is C macros produce C source code that you don't see, whereas Rust macros produce abstract syntax trees. So they create compiler objects.
Yeah. I have to say I haven't looked into Rust macros. Azrael knows them very, very well. So in this case, Printline is actually borrowing S and T. And so what that means is that they're not moved into the Printline function, they're just borrowed.
But if it's a function.
but it's not really a function.
So I can.
Yeah, you
So
go ahead.
Printline was created quite early on, and so the Printline macro, even though you're passing S and T into it, the macro under the hood just borrows from it. Later macros, they actually made it consistent where if you pass an S and T, it will actually consume it. But in this case, Printline will borrow from S and borrow from T, and when it's done its thing, which is print a string, it will release and borrow back to the caller, which is main in this case, and then you can use S and T after that. Yeah. Rust has a within a function definition, it will tell. It's explicit whether you're borrowing or moving the parameter. Yeah, and that's where you get to lifetimes.
Okay, I'll leave it there. Does anybody have any other questions? Cool. So we'll take a couple of minutes break. Maybe eat some more pizza. I think there's still plenty of pizza there. And have some more drinks. There's soft drinks as well as beer. We'll be back in a couple of minutes. But with a better flavour than mine. He's a very experienced Rust developer. And yeah, he's go for it.
Yeah. And I think Simon's a far better presenter. So here we go. Okay, so my presentation is called Why Rust? And there are 3 whys of Rust that we can look at. We're going to look at the first one, which is the canonical question: why should anyone use Rust? The other 2 whys of Rust are: why would you contend something someone does in a particular other language, and it's because you might have learned something in Rust that proves that practice in the other language is actually not good in the long term. And the third why of Rust is why are you like this, Rust? where Rust actually does some bad things, and why and how Rust could improve, or why you would not use Rust. But today we're only going to look at the first why of Rust. So why would anyone use Rust? Okay, so in short, there's good reasons. The safety at compile time, which Simon did talk about. We will see some examples. There's code ergonomics and compiler support when you're coding, which is really nice to catch a lot of bugs. And development tools ergonomics. So when you write code, there's things from most languages would have a code formatter, linking tool, build tools. Rust does these things pretty well. We'll look at how it does that. And also, Rust has good runtime performance, which Simon did show you some graphs. And those graphs are like quite nice. Well, it's quite favorable to Rust. Okay, so safety at compile time. So Rust's favorite thing to do to a developer is fail you at compile time. Because at compile time, this is the earliest point when you're writing code that you can catch a bug. Or at least that the software can catch a bug. It can't catch your bug before you wrote the code. So, so this is what Rust does best. So example, when you have 2 threads writing to the same memory location. This is in C#, I think. Yeah, I wrote this like a few weeks ago. So we got 2 threads, each of them incrementing a field by 1, 50,000 times. And when you run that, well, we run the 2 threads in parallel. What we get is not 100,000, but just paste that. You can see that we get 74,094, and we can run it multiple times. So you can see that we don't get 100,000 because we've got a race condition there.
So you've created a random number generator.
We have, which is biased towards the high end. All right, so Rust would prevent you from doing that. So this is the same program written in Rust. Unfortunately, I have not put this on GitHub yet, but I shall hope to do that soon. So 2 threads incrementing the value of a field by 1. And when we run that, No, then. Alright. You can see that Rust has given us a compile error. You don't actually need to read the message, but you just need to know it fails you before you can actually run the program. And to allow you to actually access that shared memory location, you need to go through a mutual exclusive lock. So both threads need to have mutual, each thread needs to have mutual exclusive access to a particular data location before it can read and write to it. So here's the same thing. We've put our data, let me scroll up. There, that's our data. We put it into, we put it behind a mutually exclusive lock, and there's something called an atomic reference count. You'll learn this as you learn the language, but essentially, to access your data, you need to lock it. If you got the lock, you can play with it, and so in this case, we increment the field by 1, and we do that for both threads. And when we run this, we get our 100,000, which is our correct value. All right, and not so random, you can run it twice, it's the same. Okay, so Rust is fussy, so it does this for single-threaded applications, which sounds really strange, because if you have a single-threaded application, why would you prevent two functions from writing to the same thing when there's only one thread? There can be no race condition, right? Well, it prevents action at a distance. So here's our, here's a little program in C# again. We've got two functions. Like closures or lambdas. We got many names, but if you run them individually, you can see that 0 plus 1 will be 1, 1 plus 2 is 3, and we can run that. And we do get our 3, and you can run them many times, it's still 3. But if you take this into context where instead of a simple closure, it might be a class or a service holding a reference onto some data, it mutates that data, and the second closure or lambda might be a different class holding onto a reference to the same data, and that can mutate that data. And when they do them independently of each other, they don't know that each other is mutating that data, and that's where you get your shared reference where you've got someone changing data and you don't know where it is, and that's your action at a distance. So Rust would prevent that. So if we close this one and open the Rust version, so same code, a lambda which increments the value, and if you run it, you can see that Rust will tell you the first closure has a reference to the data, and second closure tries to mutate it as well, and that's not allowed. So this is one of the things that Rust does at compile time, which prevents bugs from happening or prevents surprises. There's many other things, we'll see some, but this is probably one of the most valuable ones. Okay, so code ergonomics. So this is where, well, at least the first one, expressive syntax with checked execution paths. This is where Rust highlights when you have code paths which you have not covered, and you want to cover them, or explicitly choose not to, or you try to handle code paths which can never exist. So we'll look at that in picture form. So here's our first one. Rust supports sum types. Does anyone not know what sum types are? So sum types is like enums, but each variant can have different data. So for example, if you have, actually let's go with the inheritance analogy. So inheritance, normally you have an animal on top and dog and cat at the bottom, and so and so. So for some types, at the definition of animal, you know exactly what subclasses you have, and you when you define animal, you don't have any open-ended inheritance hierarchy. So you cannot add to animal if it's a sum type. Whereas if it's an inheritance hierarchy, say in Java or C#, your superclass, you can always implement more subclasses. So in sum types, you cannot. So what this means is the compiler knows when you define the type, all of the paths that must be handled. Whereas in an open hierarchy, you cannot know that ahead of time. So the compiler thinks it's a non-exhaustive set of paths, and it cannot tell you what you have not handled. Got that? Might be a bit hard to picture. We'll look at this little program. So let's say we've got a program specification where we take in a location, that's our parameter, and we return a currency for that location. And if we do not have currency for that location, we return an error. And if we do, we just print currency. So we'll look at this in picture form. So let's say we've got 4 locations: Earth, Moon, Mars, Heaven. I couldn't go bigger than that. But so on Earth, we got cash. We use cash. On the Moon, we got oxygen. That's your currency. And yeah. And on Mars, you might you might trade dirt because you need to plant dirt, right? And in heaven you have no currency because everything's free. Okay, so here's our program spec. We need to handle 4 input cases, and our function will take those as input. And if there is currency for that location, it will return it. One of these 3 cases. So that's a yes, we have currency, and what type of currency we have. And over here is our error case. If there's an error, we just return a string or static string, whatever that means. But point being, we have, before we've even written the code, this is our these are the code paths we need to handle, the input cases and the output cases. Those are all laid out cleanly for us. We need to now see how Rust can help us check that we have handled all of these cases. So if we express location in code in Rust, that's this thing. So it's enum location and for names, which kind of maps to your C or Java or C# enums. It looks very similar. And when you use location as a parameter, so that's our sum type as an enum, you need to handle all cases. So we've got our 4 variants, we need to handle all cases. And if we do not handle one of these cases, we'll get a compile error. So I will show you that right now. So here's the same code. Let's say I am not handling Moon or Mars. Save that. So immediately you can see that I've got feedback that I haven't covered 2 edges of this graph. So if I try to, if I put them back, Russ is happy. If I try to handle a case which does not happen, which is this unknown case here, I will get another error which says this unknown code path, you're trying to handle this unknown code path, and you shouldn't try to do that. So Rust will tell you at compile time what paths you have not covered and what paths you are covering which should not be there. All right, so that's using the enum as an input. We'll look at how it handles it at the output side. So when you use a sum type as the return value, so in this program graph, in this graph, we've got kind of 2 levels of output. So one is whether or not we had currency at a particular location. So that's our result enum. And within the OK variant, so we have currency, there's 3 code paths we need to handle. So it's very similar to the input case. If you do not handle any of these edges, Rust will give you a compilation error. And if you try to handle a case which doesn't show up on this graph, Rust will also give you a compilation error. So let's look at that in source code. So here's our, here's where we use the function. So when we look at the result, which is the return value of get currency, there's the OK path, so those 3 paths, and there's the error path, which is that path. And if we take away any of those paths, it's going to give us a compilation error. So at compile time, you have caught all of the paths that you should handle. And in most other languages, say Java, C#, Ruby, if you don't handle the error case, Java actually has checked exceptions, but for C# and Ruby, if you do not catch the error case, which usually there are a lot more error cases than correct case, the program will just compile, and it will not tell you, hey, you haven't caught this integer overflow, or you haven't caught, maybe if you're talking to Amazon Web Services, you haven't caught the rate limited exceeded exception, that kind of thing, which is, it happens more often than you'd think when you are, when you're working in enterprise software level. When you code, you're only going to code and test for spinning up one instance of one VM in Amazon. Whereas when you roll it out and deploy to production, you're going to deploy maybe 1,000 machines, right? And then you hit those rate limit exceptions really quickly. And so Rust would prevent you from not handling that. Or rather, Rust would force you to handle those cases before you actually get to compile your program. So this is one of the big advantages. So let's close that. Yeah, see that. Okay, so we've seen this too. Okay, so let's look at the next one. Actually, any questions so far? No? All right, sweet. So, so Rust also allows you to do some expressive things with your code which you don't usually get in other languages. So for example, if you want to prevent users from mutating data, like you want to give them read access to some variables, but natively those types have a mutatable they have a mutatable function. So let's say over here we've got a data class which has a value, quite simple. It's got a get value and a set value. If you pass this data class around, normally speaking, people wouldn't abuse the API and set the value when they're not meant to set the value. Whereas if you want to prevent them at compile time from mutating the value at all, say for reflection, you can create a wrapper class called data immutable, which exposes only the get and no set. And in that case, you prevent the user at compile time from ever changing the value within the data class. So Rust does this at the language level where you've got the immutable by default. And so if you have an immutable reference to some data, you cannot change the value in that data. And you can only change it if you have mutable access. So at the language level, you've got that support. Whereas for other languages, the default is you can mutate, and it does not have that language level support. You need to create your own types to prevent users from doing the wrong thing. Any questions on this one? No? Okay. languages have examples of C++ and Rust both have mechanisms of preventing users from mutating data. C++ has like this int reference const thing. Yeah, if you're a C dev, you probably know what it means. Let's go to all right. No nonsensible defaults. Okay, so Rust does not have nonsensible defaults. We'll look at what a nonsensible default is. So in C# or Java or Ruby, if you want to compare two objects, let's say you've got here data value equals 1 and data 1 value equals 1. If we compare data 0 and data 1, do they equal? It gives you back false, because by default, it thinks the equality operator should compare the memory addresses of these two objects. So like hash some pointer compared to hash some other pointer will not equal, and that's why we get this false. We could run it, but we don't have to. Same thing in Ruby. If you have a field, which is just a value int, and data 0 and data 1 both have the same value, comparing these two different instances of the same data type, you get false for equality unless you implement the equals operator. And so that's a nonsensible default because it's a surprise to the user whether or not their data type will equal each other based on the implementation. And they don't know the implementation unless someone has documented it. So I guess another way to expose that is for older languages, they have decided that memory address equality being the same as value equality is a bad default. Got that? Sweet. So Rust does not have this default. It decides, all right, if you have a data type and you try to compare it, and you have not defined how it should be compared, it will not fall back to your pointer equality. It will tell you, yeah, I do. Okay, so it will tell you, I don't know how to compare data to each other. And the only thing that you have to do to implement equality field by field is to use this macro up here. So over here, it's got derived partial equal, and the default implementation is to compare field by field. Does this instances field A equal to that instances field A, and does the same for the remaining fields. And so if you actually try to compare them, when you have the same value, then it will return true, which is what you expect. And if you actually wanted pointer equality, that's under a different function call. You have to actually go, does pointer of the first thing equal to pointer, or pointer equals to the other thing? And that's a lot nicer because you now know whether you are comparing pointers or comparing values. Yeah.
Can I just add something?
Yeah.
Yeah, so the partial equality macro, which is derived, is fully nested. So it will, even like a deeply nested data structure which inherits other data structures, it will propagate all the way down to the other ones which have implemented partial equality. So
something unsensible, it will ask you, what do you want me to do? Because it doesn't want to go, I don't know how to compare this lower level type with that one, so I'll just ignore it. That's not a good default, which might be something you might tend to do in practice, but you need to choose it in Rust. So yeah, so Rust doesn't take the easy way out.
Can you ignore a few fields, for example?
Yeah, so you can implement partial equal directly yourself. Yeah, so one thing about C# and Java, when you implement, so dev tools and ergonomics. So it's very nice to write code in Rust because so code formatting is built into the standard tools that you ship with the Rust set of tooling. So when you use the Rust stub, which is the Rust installer, by default it will give you some of the standard tools. So you've got the package manager, you've got your code formatter, and you've also got your IDE helper thing, which is called LSP. Language Library Protocol, or Rust something. Rust
RLS.
Yeah, RLS, yeah, that. So there's also additional tools which can be shipped with the default installer. I'm not sure if Clippy is, but Clippy is the thing which runs over your source code and gives you more pedantic warnings and denies. So if you do something bad, or you do something which looks like a performance issue, Clippy will tell you, hey, you should change your code from this to that. Or if you do something which is not idiomatic Rust, so idiomatic Rust being, this is how Rust developers do stuff, so you should follow them. So Clippy will tell you that. So here's an example. So if I show you this, okay, so when we have a function, ignore the docs right now. So if you have a function and we've got a return statement, which you can do in Rust, it's completely valid, and you run Clippy over that. Wrong button. All right, so Clippy would say, hey, remove your return thing and just put that in its place. And because it's more idiomatic for you to just use the last expression as your return value. It will tell you this for many, many things. There's a few hundred in the Clippy database. And it will tell you things like you are allocating memory, like you're duplicating this object, which takes a memory allocation, when you're only borrowing the value and dropping it later, which means you've wasted time copying your memory. And so that's like, it gives you like, I don't know how many milliseconds of improvement, but it tells you for everything, so that's really helpful. And you can say fail your, well, if you use Clippy in your CI, continuous integration, you can tell Clippy fail the build if any of the warnings appear, so deny all warnings. And then you can, in that way, no one can commit any code which is not adherent to Clippy's rules. Yeah. Okay, so actually, let's leave it there, and let's look at documentation. So this time we are looking at documentation. So over here we've got the source code that we saw earlier. It's actually included by a path, but anyway, here Rust uses Markdown as your docs, and in your Markdown, usually you can put code snippets. And what Rust does is it will generate your documentation from your Markdown, and it will also run the code in your code snippets. So your code in your code snippets must compile before you can pass the pass the test. And that way you know that if you're creating documentation for your users, that the examples you give to your users are actually runnable code. So you can't give them bad documentation snippets to copy paste. So that's really nice. And generally speaking, if you look at a Rust library's documentation, if the user, well, if the person, the maintainer, has put effort into the docs, generally speaking, the Rust library is going to be of high quality. So yeah, that's a really good indicator of what library you want to depend on. So we can look at an example of this. So here's my little snippet. So this will give me the docs for that set of Markdown. So returns the sum of two values. That's my add function. So the first line, oh, let me go back to the right place. This one, okay. So the first line is going to be the summary line. They generally tell you to keep it, I can't remember, 50 or 80 characters, because that will be what you get when you have a list of all your functions listed out. And if you go in there, well, we've got your headings, they're all bookmarked. And here's your example code. And this, if you publish your crate to if you publish your library to the public registry, you can click run here, and the public registry will be a source of code that this playground thing, which is an online Rust runner, it'll download your crate and it'll actually let you run the snippet of code in the browser. So that means the user does not have to download your library to try it out. Yeah, which is really handy, because sometimes you're just trying out libraries and you just want to see, can I do this small use case which I'm looking for? And
is that really in the browser, or is it on the cloud?
It's on the cloud. Yeah, so the interface is in the browser. It will ship this off to some VM somewhere, and then it runs the code in that VM, and it sends it out back here. Yeah.
Give it time, I'm sure it'll be in.
There is WASM, right? Okay, so we can also see it actually run the snippet. So this one will pass, and if I change the code to something incorrect, so here I'm adding 1 and 3, so A plus B is 1 and 3. Right, so that should be 4, and it will tell me that I expected 3, but I got 4. So this is not in color. There is a crate that makes this in color for regular tests. I'm not sure if you can do it for dot tests, but yeah, you can have like red and green or something like that. Yeah, I do like my color as well. Okay, so I think the crate's pretty print or something. Do you remember? Right. Okay, so dependency management. So if you are a C or C++ dev, you know that if you want to have a library included into your project, you need to write your own CMake scripts to download the to download the library and set up your compilation paths and put the linking flags in the right places to get it to work. Just to download a package is a whole chore in itself. It can take a whole day. It can take more than a day. If you want to do it in Rust, you can just go package name equals what version, and you can make it optional as well. So you can have code which, if you're on Windows, do this. If you're on Mac, do that. Or if the user has chosen, I want to have this feature enabled, then you build extra code into your program. So you can turn off code by feature flags. So that's real nice as well. And that's all done. This weird thing. That's all done through the package manifest, which is called cargo.toml. Yeah, it's another markup language, or Tom's obvious minimal language or something like that. Yeah.
What is the preferred way to have different code compiled depending on which platform is compiled on?
Okay, so there's
Using credits are the That's the short answer.
So there's two kind of ways. I think the better way, or at least the least painful way for users is you can in your cargo.toml say target.something.dependencies, so target.windows something dependencies, and you list your Windows crates there, and target.something else not Windows, so Linux or Mac dependencies, you can list your crates there, and Cargo will automatically, when you go Cargo build, Cargo run, based on target platform you're building on, or target architecture.
But what about code within your crate or your application?
I'm not sure which answer to give, because do you mean feature flags?
Yeah, I suppose, but so in C you'd be if def, Windows, macro, whatever.
Oh yeah, so yeah, you do have these the feature flags. So you can also say you can target specific platforms as well. So you can you've got those if defs as well, but they're not if def.
Yeah, they're like configured.
Yeah. It's pretty similar to,
So they look like macros and you put them in your file.
Yeah. And there are ways to, in CI, you can say test this combination of features. So there are crates which go for all of the features in your manifest. It will compile every single combination. There's that kind of crate which does exhaustive testing. Otherwise, there's another one called Cargo Tarpaulin, which it's mainly for code coverage, but I also use it for test these particular feature combinations. Yeah.
And you can use, like if there's some kind of GCC compiler which compiles to a specific architecture, you can plug in that compiler as well. So you can, just compile for an ARM processor or things like that.
Yeah, you can change the underlying compiler and the linker flags and all that. Okay, compilation targets. So this is about the target host that will run your program, not the thing that's building the program. So you can build from a Windows box to run on Windows, Linux. I've never tried to run on OS X. Well, I've never tried to build something on Windows to target OS X. I've seen people do from Linux to OS X and Linux to Windows. OS X to the others I've never tried, I've never seen, but I haven't looked.
Should be perfectly fine, because I think all it does is basically say to LLVM, do it for that architecture.
Yeah, and use these libraries.
Yeah.
So theoretically it would work. And yeah, that's cross-compilation for you. And if your code is mostly written in Rust, as well as your dependencies are written in Rust, usually it would work. Usually you can compile for every target platform. But if you do have system libraries, so like Linux, you might depend on, I don't know, some lib, ALSA, or something for sound, then you need to have something else for Windows sound. And you can encapsulate that in a lower level library. So users of your crate can just say, I want sound, and then they don't have to worry about the underlying implementation to switch between OSs. It will just, the lower level library will handle that for you. Yeah. And yeah, we've got WebAssembly, Simon had mentioned. This was one of the things I made this, well, for 2.5 years I worked on this. It's still not out. Yeah, so on the left we've got something written, something compiled to the browser, and on the right it's a native application. And here we've got it running and talking to each other using WebSockets. So on the left we've got Chrome, and on the right we've got Linux box. They're actually both running on the same machine. And let's speed it up. Yeah, so
how much extra code do you need to target the two platforms?
how much extra code? I didn't actually spend very much time on this one.
Like percentage-wise, roughly, like is it 5%, 10%, 50%?
5%, very little. But
yeah.
that said, most of my actually, so 5% of the code, but then the work to find out that 5% was a lot. so I had to figure out, all right, these libraries, so to debug this in web browser is actually quite difficult. You just get panics, and panic is like one of the things the windowing library does on purpose to get the Rust code to be given over to the browser. But anyways, it's very hard to find which 5% and how to solve that 5%, because you need to go and tell your code be compatible with the browser's safety guard. So like audio, you need to have a user interaction before the audio can start playing. What else? Like networking, you can't just create a UDP socket. You need to use WebSockets or WebRTC. This uses WebSockets. Yeah, and loading stuff. So loading files, that was, you can't load stuff on non-main thread or something, or at least you can't create threads from the non-main thread. So you might say create a thread to load this thing and wait for it, but then the thread was never created in the browser because the browser doesn't allow you to do that. You need to return control to the browser, and then the browser will create it, which is, it's a lot of pain, but yeah, you can do it. It just takes a lot of time to figure out what you have to do. Yeah. Well, all right. And I think we've got the last one, runtime performance. So you saw in Simon's presentation, we've got very good performance from Rust. There's two benchmarks. The Treep one is probably a better repository to look at because it compares what idiomatic code written in each language, so idiomatic Python versus idiomatic Rust, idiomatic C#, idiomatic JavaScript, what a regular developer would normally write. Those benchmarks are compared to each other, and they also do, all right, if we do the worst possible thing in every single language to squeeze out the most performance you can, what speed can we get out of each language as well? And so it does those two different types of comparisons. And we can look at the results. So C++, I think, is the fastest. So if we look for so this table, so the tune implementation scoreboard is where they try to make things as fast as possible in each language, ignoring best practices, ignoring safety. And C++ wins. Rust is not too far back. Let's go down. Yeah, so it's 20% slower than C++. There's no GC, so you don't get your GC pauses in web applications. Not that I know of any big web applications using Rust, but yeah. And high performance is achieved through native code, so using the LLVM backend. So if you think of it, Rust or C or C++, they all are different languages at the top level, but they emit some middle implementation which is input to LLVM, and that's what gets compiled to machine code. So how they do that middle output is up to the Rust C++ compilers, but generally speaking, a lot of the optimizations happen at the lower level as well. There's zero cost abstractions, so if you have types, so let's say you define a new class which wraps a different class. If you use a language like C# or Java, you've got that runtime information which slows down your program a little bit just because it's got another type to dereference. Whereas in Rust, it's all paid at compile time, so it will not think of it as another type. It's just going to be like your inner string. And there's also control over memory. So for size types, so types that it knows the size of, if you know data layouts and stuff, it allocates memory on the stack, which is a lot more performant than allocating memory on the heap. Because on the heap, it needs to ask for it and get it needs to find space in your heap memory to actually allocate that amount of memory. Whereas on the stack, it just knows, oh, you've got this specific size, which it has computed at compile time. So it's a lot faster to use stack memory. And also it encourages sharing memory references instead of cloning. So you don't duplicate memory, which takes time to allocate memory. Whenever you write code, it will tell you can use a reference instead of cloning the memory. So you get performance from there as well. Cool, and I think that's what I've got. Any questions so far? No? Alright, so I've got some links at the very end. Oh, okay. Yeah. So there's the main website, and there's the RS, which is the installer, and the beginner's guide. And all of that is actually very user-friendly. I think out of learning many programming languages, this was the one where I just went to official resources and I didn't need to look for people's blogs to understand stuff as much. Yeah.
Cool. Thanks, Azrael. So yeah, thank you guys. Does anybody have any questions for Azrael? Cool. So it's another meetup. Next month we hope to continue another session of this type. So it's kind of introduction to Rust, as well as I hope to get some people to speak about some projects which they've been thinking or working on during lockdown. I don't know. If you have any projects which you've been working on in Rust or something around that theme, let me know. I'd be glad to hear. And this needs to be something short, 5 minutes, 10 minutes, or 1 minute. But otherwise, thank you guys for coming. And next meetup will be on the 7th of December. Cool. And we'll also do a bit more introduction to Rust as well, so you get to know about data structures and enumerated types and just a bit more detail. Cool. Cheers, guys.